Hello everyone, this is Dr. Fan. Many students would get stuck when they work on Pulley systems with friction, and very few teachers at school actually discuss how to solve Pulley systems with friction. And the key thing to understand the Pulley system with friction is to know the tension on both sides is not the same. And let's discuss it today. Alright, now let's look at the Pulley system with friction. If we assume big M is much larger than small m, so the whole system would go clockwise. So big M is going to go down and the small m is going to go up. In this situation, we also say there is friction between the pulley and the string, okay? But the string is massless. So string is massless. So how do we actually solve this problem? We first start with free body diagram. So for the big M, we know it is under gravity, mg going down, and we know there's a tension pulling it going up. Let's call it Ft1, okay? And for M2, we know there's gravity, mg going down, and there's tension Ft2 pulling up. Now we can write down Newton's second law for both big M and small m. So for big M, we have the net external force equals to big mg minus Ft1 equals to big M times acceleration. And for small m, we have the net external force equals to Ft2 minus small mg equals to small m times a. We discussed it in the previous video. This acceleration has to be the same, otherwise the string will break. Alright, now here's the key thing. Why the tension on both sides of the pulley is not the same? In order to understand that, we need to know how friction works in this case. We know friction is between this part of the string and my pulley. So this part of the string. So I will take this part of the string as my system, okay? So I will consider that small piece of string which is in contact with my pulley as my system. So if I consider this part of the string, I know this string is under tension from the right. So there is Ft1 on the right. I know there's a tension Ft2 on the left. We also know the string is going to follow the whole system go clockwise. So there is a friction going counterclockwise, right? Let's just call this friction here. So then for this piece of the string, we can say the net external force equals to Ft1 minus Ft2 minus Ff equals to the string's mass times acceleration, right? Okay, now let's evaluate this equation here. So some student might say it's the same string, so the tension on both sides would be the same. Let's consider if that's possible. If we let Ft1 equals to Ft2, then the net force becomes minus F equals to mass times acceleration. So this force is going counterclockwise. That means this part of the string is going counterclockwise, which is not possible because we know the whole system is going clockwise. So what should be the net external force on this part of the string? There's one very important information in the question we didn't use. That is, the string is massless. That basically says my ms is 0. Then that basically says my net external force should be 0. In other words, the net external force on this small piece of the string should be 0. As a matter of fact, for any massless object, the net force on it should be 0. Why? Because Newton's second law says acceleration equals to net external force divided by mass. If there is a net external force and the mass is approaching 0, that means your acceleration is approaching infinity. We know that's not possible. So for any massless object, the net external force on it should be 0. Now we have 1, 2, 3 equations. And then if we add them together, let's see what we will get. So 1 plus 2 plus 3. Let's put all them together. So we get big mg minus ft1 plus ft2 minus small mg plus this third equation here, ft1 minus ft2 minus friction. And on the right, I will only get these two terms because this is 0. So I get big M plus small m times acceleration. This equation may look very busy, but actually many terms can cancel out. So tension here cancels out, tension here cancels out. So what I get is big mg minus small mg minus friction equals to big M plus small m times acceleration. When you look at this equation, let's call it equation 4, you realize this equation can actually be obtained by just considering the whole system. What do I mean here? If you consider big M, small m, and the string, everything included in your system, then along the string direction, right, you only have gravity pulling the whole system going clockwise, and this gravity on the left side pulling the system go counterclockwise, and also the friction along the string direction resisting the clockwise motion. So your net force is big mg minus small mg minus the friction, and which equals to the mass of the whole system times acceleration. So this is how you solve Pulley systems with friction. The key thing here is the tension is different on both sides, but considering friction, the net force on the string should always be 0. Many students would find it very hard to understand why I have the same string, but the tension on both sides are different. Let me show you one very good example. In many machines, you see this pulley system. There could be a belt or the chain around the pulley, and you have a driver pulley and you have a driven pulley. And when this pulley system works, it's very clear there's one side which is very tight. There's another side which is slack. And based on your life experience, you know this side, the tight side, should have a much larger tension compared to the slack side. And the key reason is because there's friction between the pulley and the belt or the chain. So this is a very common thing happens in pulley system in reality. Alright, so if you understand what we have discussed, you should be able to solve this question by yourself. So this is a question from College Board. Many students would get stuck in this question. If you also understand what we discussed, you should be able to solve this double pulley system with friction. And you would realize this question right here is very similar to the pulley with friction system we just discussed. Alright, hope you find this video helpful. I will see you next time. Thank you.